Kaya Wanju, everybody. Welcome to this, which is our third or fourth seminar in the Noongar season of Nakuru. I'd like to begin by acknowledging that we are meeting on the lands of the Wajak Noongar people and pay my respects to their elders, past, present, and emerging. So today we have the first of our ASA ICRAR Symposium speakers. So this is a program run by the ASA where ECRs get to submit abstracts for seminar organisers around the country to read. Any PhD students or later on ECRs who have not submitted for these kinds of ballots, I would definitely encourage you to do so, because it means that you get to share your work in places that you wouldn't necessarily have visited before. And this is how we have the pleasure of hearing a talk from Sajay Mathew, who is a PhD student over at working with Christopher and Amit Sessa. So I'm going to hand over to Amit, to Sajay. I'll get there eventually, won't I? Thank you very much.
Yeah, thanks, Kate. So hi, I'm Sajay, and I'm a PhD student at the Australian National University, and I work with Amit Setta and Christopher. And this talk will also include results from collaboration with Su, who's from University of Florida. And before I start, I would like to acknowledge the traditional owners of this land where we work, and I would also like to extend my respect to the elders past, present, and emerging. I would also like to thank Kate and the seminars team and also the ECR Symposium organizers for giving me this opportunity. And I would also like to thank Lainey for helping in organizing the trip. So, the astronomy department of ANU is the Research School of Astronomy and Astrophysics, and it's located at Mount Stromlo. And Mount Stromlo is within the Stromlo Forest Park. So every time you drive up the mountain, there'll be a million kangaroos there staring and judging you. And ANU and also Mount Stromlo is located in Canberra. And Canberra is a relatively quiet place, but it still has some fun events like Floriad Fest, which is a festival of flowers. And there's Enlighten Festival, where you get to see a dozen hot air balloons going up simultaneously. And about things to do in Canberra, you can do hiking. There are a lot of really nice lookouts, and it has easy hikes. And there's the Questacon, which works for all age groups. And then there's nothing much else that. And we have beautiful weather in Canberra. It's just a day. Yeah, but jokes aside, Canberra is a really nice place. I don't know why, but I still love Canberra. Okay, this is science. So, like I said, I study star formation, and this is an illustration of Milky Way, beautifully mapping out its spiral arms. And it is this spiral arms where the star formation takes place, and the spiral arm holds really high dense regions of gas comprising mainly of molecular hydrogen, and these regions are called molecular clouds. And this is an example of a giant molecular cloud called the W3 complex, which is captured by Herschel. Molecular clouds like the W3 host accumulations of cold, gas, and also dust, which are extremely dense. And these accumulations are called dense cores. So the dense cores are the birthplace of stars. When a dense core becomes gravitationally unstable, it collapses to the center, raising the density in the inner regions. And since the dense cores have some inherent angular momentum, instead of all the gas falling really inwards, most of the gas actually forms a gaseous disk, and the central parts accretes the gas through this disk and gaining in mass. And with time, the central region of the inner parts later evolves into a protostar, and the gaseous disk or the accretion disk fragments into planets. So that's the simple picture of star formation. And I'm mainly focused on what sets the mass of a star during the star formation process. And this is directly linked to the mass distribution of stars, because stars always form in clusters. And this mass distribution is called the initial mass function, or the IMF. A remarkable feature of the IMF is that it is found to be relatively universal. That is, if you compare the mass distribution in two different star forming regions, you'll find that the functional form is almost similar. There are two commonly reference forms of the IMF. One is the Chabry IMF, which is a power law in the high mass end, but it then smoothly transitions into a log normal form at subsolar masses. Then there's the Krupa IMF. This is similar to a Chabry IMF, except that instead of a log normal plus power law form, is a three-segmented power law. So if you look at the figure, the reason why the power law is a straight line and the log normal is a version is just because that we have a logarithmic scale. And two important characteristics of the IMF is that the peak of the IMF occurs at around the quarter the mass of the sun. And also in the high mass range, the power law has a slope of around minus 1.3. And this slope is called the Salpeter's law, because it was Salpeter who first found that the high mass can be described by a power law with this slope. Because of the apparent universality of the IMF, it has many applications. The birth mass or the initial mass dictates the life history of the star. It is used for determining the star formation rate, for measuring the chemical abundance and the total energy output of the star cluster. And it is a central ingredient in studies of dynamics and evolution of galaxies. And it's also sometimes used for evaluating cosmological parameters. And because of these applications, there have been many measurements of the IMF. You can see that in the high mass range, most of the data points lie very close to the Salpeter slope, and also the slope of 0, which represents the peak of the IMF, lies around a quarter the mass of the sun, which is around 0.3 solar masses. So even though you can see these features, you can still see that the scatter is non-negligible, and there are a few outlier IMFs as well. So one of the main outstanding problems of the IMF is that, we are still not able to explain the Salpeter slope in the high mass end, and also what is the origin of the peak of the IMF, and also the reason for outlier IMFs. And this is because star formation is still not fully understood, and that in turn is because the star formation process is a highly dynamic process that involves a wide range of physical mechanisms, including turbulence and magnetic fields. Also, stars interact with their surroundings through stellar heating and protostellar outflows. Also, the effect of these mechanisms on the star formation process and also the IMF is interrelated. So to give an example, this is the W3 complex I showed earlier. Adjacent to this complex are W4 and W5. So the cavities that you see here are formed by the stellar feedback, and the bluish glow is due to stellar radiation. The cavities actually allow the stellar radiation to escape out to larger distances and influence a larger volume of gas. Also, the stellar feedback drives turbulence within the cloud, creating short regions of gas, allowing more stars to form. So this shows that star formation is a very complex process, and the effect of these mechanisms are interrelated. So this means that to accurately model star formation, you need to incorporate all these mechanisms simultaneously. So in my PhD research, the main aim is to study star formation through numerical simulations, where we take special care to take into account all these mechanisms. We include all these mechanisms simultaneously in the simulations. So I'll give a brief description of the simulation setup. All the simulations are performed in a three-dimensional triple periodic computational box of silent 2 parsecs. Initially, the gas density and the magnetic fields are uniform, and the total cloud mass is around 800 solar masses. Although in the initial stages, both the magnetic fields and gas density are uniform, we stir the gas in the box using our turbulence driving module. What this does is it actually sweeps the gas around and creates a turbulent statistics that mimics the turbulence in real molecular clouds. And this turbulent motion also modifies the magnetic fields due to the stretching, twisting, and the compression of the magnetic field lines by the turbulent motions. Once a steady state of turbulence is reached, we turn on self-gravity, and that's when stars start to form in the high-density regions produced by the turbulent shocks. We allow the simulations to evolve to a star formation efficiency of 5%. That is 5% of the total cloud mass has formed stars. So once the star formation efficiency or SFP of 5% is reached, we look at different statistics like the initial mass function and also star formation rate. So since we include a lot of mechanisms in the star formation process, and also we use high resolution grid for the simulations as well. This means that the simulations are computationally expensive. To run the simulations, we make use of the supercomputer GADI at NCR, which is located in Canberra, and also Setonic Z4C, which is housed here in Perth. So let's start with the effect of the stellar heating. Stars in the early stages have high luminosities, and because of this, it can influence and interact with the surroundings and raise the temperature in the surrounding medium, raising the thermal support. And because of this thermal support, the fragmentation is suppressed. So instead of a clump fragmenting into multiple stars, there's just a few stars, and these stars just accrete the whole mass, allowing it to grow to high masses. To accurately model the stellar heating, we need to self-consistently solve the radiator transfer equations. But this in large-scale simulation is impractical because you need to trace rays from each and every grid cells. So what we do is we use a semi-analytical model, which is based on previous radiator transfer simulations and also observations. So the figure here on the right is an interesting comparison between the temperature structure around the stars in our simulations with the protostar in a cloud in Taurus, which was recently captured by JWST. So the heating is mainly in this region, there's like a conical shape, and that's because there exists the accretion disk around the stars, and the accretion disk contains dust particles, and these dust particles absorb the radiation from the stars and shields the outer regions of the accretion disk from the heating. So the heating is mainly in polar directions. So this is the model that we use in our simulation called the polar model that takes into account this effect of the optically accretion disk. The figure on the left shows the comparison in the number of stars formed and the average mass obtained in 3 different simulation models. In the first model, there is no heating, there is no stellar heating. In the second model, the heating is spherically symmetric, and the third model contains our polar heating model, which takes into account the presence of the accretion disk. And you can see that the number of stars formed and also the average mass changes on changing the heating model, which means that accurately modeling the stellar heating is important to obtain accurate results on the diagram. So what do jets and outflows do? So stars also eject part of their accreting material in the polar directions, and these are referred to as the mechanical outflows or the outflow feedback. And the outflow feedback comprises of 2 components. First is the highly collimated stream of gas called jets, and then it also has a wide-angled and low-speed component. The outflow feedback is actually a result of the interaction between the magnetic field lines close to the stellar surface and also with the accretion disk. And to self-consistently model the outflow feedback, that's a bit tricky situation because all this physics happens close to the stellar surface. And in large-scale simulation, and it's not possible to resolve down to those scales. So we use, again, a subgrid model or approximation model, which is a very common practice. The figure here is a zoom into a high-density region in one of our star formation simulations, both in the presence of the outflow feedback and also in the absence. The top panel shows the gas density projection, and the bottom panel shows the temperature structure. The circular markers that you see are the stars. The size of the markers is scaled to the mass of the stars. So if you look at the simulation with no outflow feedback, you can see this is like a really large filamentary structure, and there's a few stars accreting from these filamentary regions. But when you compare it with the simulation with the outflow feedback, you find that the filamentary structure breaks into multiple fragments, and also the mass of the stars is lower, and there's more number of stars. This is because the protostellar outflows perturb the accretion flow to the existing stars, creating multiple accretion channels and allowing more number of stars to form. If you look at the temperature structure at the below, the heating is more efficient in the simulations without the outflow feedback. And that's simply because in the simulation with the outflow feedback, there's a mass loss. So the mass of the stars are lower, which means the luminosity is also lower, which means the heating is less efficient. So this again shows that the effect of different mechanisms are interrelated. In terms of the IMF, we find that the inclusion of the outflow feedback shifts the IMF to lower masses by a factor of 1/2 without changing the shape particularly. So this means that the inclusion of the outflow feedback is important to reproduce a mass scale of the observed IMF. Turbulence. Molecular clouds are supersonically turbulent, and it is found that turbulence in molecular clouds is found to play a dual role. That is, on the large scales, it provides an additional support due to the extra kinetic energy, while on the smaller scales, it enhances fragmentation and formation of stars because of the turbulent shocks producing high density regions in the form of filaments and clumps and allowing stars to form. Also, turbulence is mainly driven on the large scales in the molecular clouds. That is, most of the energy is on the larger scales, but it naturally cascades down to smaller scales in the form of a power law. And turbulence in interstellar medium can be defined by a combination of two modes of turbulence driving. One is the purely compressive driving, that is curl-free driving. Like the name suggests, it's basically just compressions or refractions. So an example would be hitting symbols together. And the next mode is the purely solenoidal driving, that is the divergence-free driving, and the example is stirring a cup of coffee. So this is an observation measurements of turbulence driving in different studies. I'll be happy to explain how the turbulence driving is measured. But for now, I think what is just important is the data points that lie close to the dotted lines means those are the clouds where the compressive driving is dominating. And the ones close to the dashed lines have clouds that are dominated by solenoidal driving. And the straight line is the mixed driving, that is the equal energy in the compressive and solenoidal driving. So this comparison is between a set of simulations where one employs purely solenoidal driving and another employs purely compressive driving. You can see that in the purely compressive driving, the structures formed are really large in size, and also density is also high. So as soon as self-gravity is turned on, stars start forming aggressively. While in the case purely solenoidal driving, the structures are relatively small and the density is also lower. So when this gravity is turned on, only a few stars form in the early stages, but later more stars start to form due to the because some of the structures merge together due to the turbulent flow or due to the action of gravity. The star formation rate of purely compressive simulations is found to be an order of magnitude higher than that of purely solenoidal driving. In terms of the IMF, we find that changing the driving from a purely solenoidal to a purely compressive driving, the IMF, there's more number of low mass stars forming and the characteristic mass shift to lower masses. So to quantify or to ensure that the variations that we see in the IMF is not due to the binning choice, we fit a modified version of the Chabrier IMF to our simulated data. The modified IMF is similar to the standard Chabrier IMF, except that in the power law tail, we add an exponential factor to take into account the finite mass in the box. So this basically introduces a cutoff at high masses. and the different parameters of the fit. For example, the peak of the IMF, the width of the log normal part, and also the slope of the high mass end are all derived using MCMC sampling. And the advantage of this is that the MCMC sampling takes as input for the algorithm just the list of masses and not the bin data. And you can see that the fitted curves fit very well with or agrees very well with the simulated data, which justifies our winning choice. And the median mass of the polynomial simulations is found to be 1/5 of purely compressive driving. And this change is not a big change, but the important point is that time is still sensitive to the turbulence driving. And another important cloud parameter that is associated with turbulence is the cloud virial parameter. The virial parameter is basically a ratio of the kinetic energy to the potential energy or the gravitational energy. Virial parameters of less than 1 means that the object is gravitationally unstable, that is, it is prone to collapse. And virial parameters of greater than 1 means that the object is unbound. So the figure here shows some observation measurements of the virial parameter in different clouds. And you can see that most of the data points lie very close to value of unity, but still there's a large scatter, and it shows that the virial parameter can actually change by more than an order of magnitude. So how does this changes in the virial parameter affect the star formation process? So here I show a movie comparison between 3 different simulations models where the virial parameter changes from 0.0625 to virial parameter of 0.5. If you look at the right panel, which is the virial parameter of 0.5, you can see that there are mainly 3 star forming regions, and which are really highly dense. So with time, as gravity becomes stronger, these high density regions fragment into stars. While if you look at the other panels, which are the lower virial parameter ones, you can see there's more fraction of star forming regions and it is more networked. This is because when the virial parameter is lower, the gravity is relatively more dominant, and this kind of enhances the ability of gravity to amplify the anisotropies produced by the turbulence, creating additional filamentary or clumpy structures and leading to more number of star forming. So the virial parameter, so the star formation rate of lower virial parameters is found to have like much higher star formation rate. In terms of the IMF, we find that the main change is in the peak of the IMF. And you'll see that there's a systematic change in the peak of the IMF on changing the virial parameter. That is, if you change the virial parameter by a factor of 1/8, the peak of the IMF shifts by a factor of 1/2. And this again is not a big change, given that the virial parameter changed here by a factor of 1/8. That is, the dependence of the IMF on the virial parameter is weak. And this is what we saw before when we looked at the turbulence driving. The effect of the turbulence driving on the IMF is also weak. But like, what happens if we change more than one cloud parameters? So we looked at an experiment where we changed both the virial parameter and the driving. In the first model, the virial parameter is 0.5 and the driving is mixed, that is equal power in the solenoidal and compressive modes. And the second model, the driving is same, that is mixed, but the virial parameter changes by a factor of 1/4. And in the third model, we change both the virial parameter and the driving. The virial parameter decreases to a factor of 1/4, and the driving changes from mixed to compressive. So when we change both the virial parameter and also the driving, we find that the peak mass shifts to lower masses by a factor of 3. So this change is comparatively bigger when we just changed one of these parameters. That is, before we changed the virial parameter by a factor of 1/8, so it produced only a change in the peak mass by a factor of 1/2. But here we see that it changes by a factor of 1/3, even when the virial parameter decreases to 1/4. The thing is that because we changed the driving as well. So what does this mean about the IMF measurements? Also, you can see that the slope of the IMF is much more shallower in the case when we change both the driving and the virial parameter. And what does this mean for the IMF measurements? So our results suggest that the scatter that you see in the IMF measurements is due to the weak difference of the IMF on the cloud parameters. So most of the IMF measurements are done in the local universe or the local neighborhood, and these star forming regions are in the same environmental conditions. So the cloud parameters does not change much. That's why the IMF measurements or the IMF form are very similar. And the outlier IMF may be due to the combined effect of the cloud parameters. And this is the reason why it is highly probable that the early galaxies might have a different IMF, because here the early galaxies would have more than one cloud parameters. Different. For example, the turbulence might be very different in the early galaxies compared to the solar neighborhood or the local universe. Also, the metallicity is very different. And another important parameter is that the magnetic field structure should be also very important, which we still need to understand more about. So the idea is that, one of our next studies that we'll be performing studies on the magnetic field structure. That is the effect of the magnetic field structure on the IMF. And the idea is once we complete all these studies, we would have completed or finished a large parameter study, and this would allow us to provide important insights into the origin of the IMF. Yeah, and also our studies have important implications on galaxy formation. Most of the galaxy formations simulations employ a subgrid model or approximation model to take into account the total energy output from the star clusters. And that's because since these galaxy formations are really large scale simulations, you won't be able to resolve down to individual star clusters or stars. And in these models, one main assumption is the universal IMF, but we show that the IMF is dependent on the cloud parameters. So this would mean that the energy output from this in this model should be different when we go to different regions of the galaxy. In addition to the IMF, the changes in the cloud parameters can also affect the binary statistics. On the top plot, I show the multiplicity fraction as a function of primary mass. Multiplicity fraction is the ratio of multiple systems like binaries, triples, and higher orders to the total number of systems. A multiplicity fraction of 1 means that all the stars are bound to at least one another star. That is, all of them are binaries, triples, or higher order systems. And a multiplicity fraction of 0 means that all stars are singles. That is, none of them are bound to any other star. In observations, it is found that the multiplicity fraction is it's a strictly increasing function of the primary mass, and our simulations also confirm the same. But what we find is that when we change the turbulence driving, the multiplicity fraction is much more higher in the case of purely compressive driving as compared to the purely solenoidal driving. And this would have implications on n-body simulations. Also, one of our recent studies show that the orbital eccentricity of the binaries, the eccentricity is a measure of finding out the shape of a binary orbit. Eccentricity of 0 means that it is a circular orbit. Eccentricity of 1 means it's parabolic. And eccentricity greater than 1 just means unbound. Values between 0 and 1 means it's just elliptical shape. So we find that the eccentricity distribution is dependent on the turbulence driving, and our simulations that employ purely compressive driving produce higher fraction of high eccentricity binaries than the mixed and solenoidal driving. And this also has implication of n-body simulations, because many n-body simulations assume universal eccentricity distribution. So, but we show that that might not be the case. So, yeah, and yeah, as I mentioned, so yeah, the scatter that you see, the scatter that you see is due to the change in the cloud parameters across the neighboring clouds, and the outlier IMS may be due to the combined effect of this combined effect of multiple parameters changing. That is like cascading effect. So my next study, one of my future studies would be to understand what is the why we have this power law tail and why is that we have a salpeter slope, and also explaining the peak of the IMF. And also I showed that these studies have implication on the galaxy formation, and that what that means is that the studies on the large scales, that is the studies of galaxy formation and evolution, are not mutually exclusive to the studies on the small scales, that is studies on the star formation. And another future work would be to combine these two scales, that is the large and small scale, that is apply the insights from the star formation study into the studies of galaxy formation and evolution. I don't have a summary slide, but I'll show visualization of the simulations in 3D. And that's one of the fun aspects of my study. And this visualization would have all the key points from my talk. Yeah, these visualizations are made for outreach purposes, so they're a bit put there. It's
Thank you for grabbing the lights. I'm sorry for missing out. There was the sharing screen thing the full time. I'm so sorry. Excellent. Questions to Sajay. I'm going to take questions from students first. And if there are any students online as well, if you can put a little raise hand symbol, that would make that easier.
What are the biggest stars that you are getting in your simulations?
So our biggest stars are close to 10 solar masses, and that's because we are because of the finite mass in our box, because we just have like 800 solar masses. Yeah. So the main thing that we're looking at is the characteristic mass, that is the peak mass. In the high mass end, because we just have a maximum masses of around 10 solar mass, the region in which the power law is fitted, it's really narrow. So that's why we don't actually do a lot of inferences on the slope of the.
Could you talk a bit more about that top plot? Why there's a difference between when you have purely compressive versus purely solenoid, or why that's such a difference on multiplicity?
Yeah, so the most probable reason is that since it's compressive, it kind of have the effect of just bringing all this gas together. And this means that in the solenoid simulation, it's all the high density regions are scattered. While the compressive, you have all these gas reservoir, and it's highly dense as well because of the compression effect, which actually allows the stars to fragment. Because from what I see is that higher density doesn't mean that the stars can reach really high masses, because usually you would expect that higher density means higher accretion rate, so it can reach higher masses. But the thing is that higher density means that it's just more probability of fragmentation, so there's like more stars forming, so more multiple systems can form.
Cool. I get Matt, Sabrina, we'll come this way around. Matt does.
Thanks for the talk. That's really cool stuff. How would you go about implementing this in like a cosmological simulation? I guess you would know the density or maybe magnetic field strength of a gas cell, but how would you actually apply this in a cosmological simulation?
The IMF or just the multiplicity?
Yeah, I guess the IMF would change.
So the IMF is mainly, since like the cosmological simulations employ the subgrid models for this like star cluster or maybe like galaxies. The main important like implication would be that the changes in the IMF in different star forming region would mean that the energy output is different, which means like the effect of the supernovas would be different, because like when the IMF is different, the high mass end would be different as well. So there'll be changes in the number of high mass stars, which means there's a difference in supernova effect as well. And this could definitely change the galaxy evolution.
I'm guessing that it would be easier to implement in a SAM than a. I guess my question is related, and it's related to how this impacts things at the galaxy scale. You talked about the fact that high redshift in the early galaxies is a little bit different because of metallicity and different turbulences. But if you even look at a galaxy population at like a fixed redshift, is it the case that when you've got a sufficiently massive star-forming galaxy, you've just got sufficiently many clouds such that you average over populations, and that's more standard, whereas at low stellar masses, you've probably got more stochasticity and therefore more variation in your IMF? Or are there underlying things going on that you might expect within a galaxy population at a galaxy level IMFs to change more depending on the type of galaxy you have? If that makes sense, it's a question.
I think so. So I think the idea is that when there's like this energy output is different, the supernova effect is different, and it is the supernovas actually kind of like creates these like short regions of gases, which allows the formation of more numbers of stars. That is the next generation of stars. So when this energy output is different, like even the next generation of stars forming would be different as well. So it can actually affect like the neighborhood cloud regions, like in terms of like there's a new cluster forming.
But if you've got like a very massive galaxy that's got obviously lots of cloud regions, do you expect there to be some sort of driving galaxy property that uniformly influences the cloud properties throughout the whole galaxy, or is there sufficient variation such that on average these things are mostly similar at the galaxy scale?
I think on the galaxy scale, one big difference is that it's found that in the center of the galaxies, for example, the turbulence driving is solenoidal, while in the outer regions it's more like compressively driven. So like since like based on what we looked at, diamond shapes are different as well. So like there can be like a spatial variation as well, just because the cloud parameters are different in these different regions. Yeah, and one of the most probable reason that like for example in the central regions we found that diamond is a bit more top heavy, that is more higher fraction of high mass stars. That would actually be because in the central regions the driving is solenoidal, and also the temperature is much more higher. So in the simulation that I showed, you can see that the solenoidal driving, there's a model of like the star formation rate is really low. The density of the structures are formed is also really low. So initially, only a few stars form, which means that there's less fragmentation. So the stars that form in the early stages, can actually like keep on accreting because it's not being fragmented. So they can reach high masses. And when they reach high masses, the luminosity is also high. And since the average temperature is high, like the whole cloud becomes a lot more warmer. And more warmer means there's more thermal support, which means that there's like again there's fragmentation. So which can actually allow these stars to again form to higher masses. So from the studies that I looked at, the main thing is that the high mass stars reach those high masses just because they form the early stages and like, are able to accrete to higher mass just because there's a lot of time period. Yeah. So like if there's no fragmentation, they can keep on going to high masses. So it's kind of like a cascading effect. So that's why I think there's like the outlier EMF can be explained by multiple factors playing into play. For example, in the center, it's basically the solar driving plus the increase in the temperature.
Two questions. So you talk about the radiative and mechanical heating of the gas. How do you handle the cooling of the gas in the simulations?
So right now what we have is a polytropic equation of state. So that is based on previous radio transfer equations. So what is it is basically the pressure is actually proportional to the density times some polytropic exponent, and the value of this polytropic exponent changes based on the densities. So when it's like really highly dense regions, the value would be there'll be like more pressure just because the density is increasing. So but one thing is that since we can't resolve down to like really small scales, so like so our stars is basically, so like for modeling stars you use something of sync particles. So and in the sync in our case the sync particle is basically star plus disk system. So we are not able to resolve down to the smaller scales. And it is in the smaller scales where there's like this adiabatic happening. So even though we use a polytropic equation of state, the system is basically isothermal. But that's still okay because like we are looking only at the IMF and we don't actually have to look at this like stuff that happens like very close to the center of the stars.
So connected to those sync particles, do you trace binarity, as in stars that form next to each other and might be gravitationally locked?
Yeah. So for creating the list of multiple system, what we do is kind of follow algorithm. So first we have a list of the single stars. So like from our simulation, what we get is like just a bunch of stars. So in that list, we find the most gravitationally bound pair of stars, and then we kind of like pair them into one object. So one object is binary. So initially, if we have like 10 single stars, when you find the first pair, and you just kind of like convert into another binary object, you just now have 9 single stars and one binary star. Then in this new list, we again find the most gravitationally bound pair. So if it's between the next bound pair is like a binary star plus single star, it would form a triple system. So this iteration keeps on going till none of the stars are bound to each other, or the highest possible system is highest possible system is quintuple, because we don't want that high order systems because with time they are going to anyway decay. So it's like we look only till like quadruples.
So have you been counting it as a fraction of various simulations in terms of solenoidal versus aggressive, for example, in terms of not fraction of binarity? Or
here it's like the blue ones, so the box on the top correspond to the purely compressive, and the bottom ones.
Oh, I see. I didn't realize that was got it.
You can see that there's actually a difference in multifraction in every mass range when you change the
Thanks for the very nice talk. So going back to Uma's question about your limited eye mass. So at the moment, due to the volume of your simulation, you don't go above 9 or 8 solar mass. Is it possible that the feedback from the high mass star that you are missing would affect the shape of the IMF in your mass region?
So there have been like other studies that looked at the radiative feedback actually kind of like changes the shape of the IMF. because it's the radiative feedback that actually kind of disperses the cloud and prevents any more stars forming. But it is found that the shape of the IMF is almost like kind of like stable, as in like in terms of the peak and also the high mass, and that is the radiative feedback happens very late because the stars, like I said, the high mass stars reach to high mass because it forms initially and just keeps on accreting. So it's only at the end of this like the whole cycle that it reaches high mass. So they are not able to affect the So it's because we don't include the radiative feedback, we stop the simulations at 5% because that's when it's like
Have you thought about comparing the morphology of your gaseous structures to observations as well?
Morphology, like we haven't done a quantitative study. Yeah, the one thing. Yeah, the one thing that we could actually confirm with observation is that like the recent observations again find that like in some observations what you see is just like filamentary structures like when you observe, and like in some stages what you see is kind of these like hubs where like it's kind of like a clumpy region and there's like this like all these stars or like gases going into these hubs. So one reason why there's this like difference in those like morphology that you see is because in the initial stages, for example, if you see in the solenoidal or like solenoidal simulation, initially what you see is actually just these filamentary structures. But if you keep on evolving these simulations, like all these filamentary structures actually merge together because the gravity is becoming more and more dominant because there's more number of stars forming. And so it kind of like brings all the gas together and creates this, like you can see now we have like a kind of this like hub structure. So that's actually just shows this like morphology is also dependent on the time. It's like the morphology changes depending on what point of this star cluster phase that we look at.
Yeah, I think there's a lot of observations you could potentially compare to. Are those column densities for H2 realistic values? I don't have a good feeling.
Yeah, they are column densities. Yeah, they are. So sorry. So the initial conditions.
Sorry.
So the initial conditions that we set is very like kind of like the typical Milky Way conditions.
Right, and then can you produce maps of CO and dust maps and stuff as well to compare the
No, we don't actually. Yeah, we don't actually follow the chemistry as in like different metallicity. It's just basically this whole like H2. Yeah.
What is the time since the beginning until the measurement of the IMF that you made in the simulation?
Sorry?
What is the time since the start of the simulation until the time you measure the IMF properties?
So the time equal to 0 here means that's when we like turn on self-gravity. So in our initial phase is we actually drive the turbulence. So we need to drive it for like 2 turnover times so that we have it's like fully developed turbulence. And then when it's fully developed, we turn on self-gravity. So that's the T equal to 0. From T equal to 0 to star formation efficiency, like you can see it's like, for example, the solenoid it's around like 1 million years. And this like time actually depends based on the different cloud properties because the star formation is different in different like turbulence travel. Yeah. For example, if you compare the
presentation, it might actually keep it fixed.
You can see in the purely compressive, like almost a star formation of 5% is reached at around like 0.2 million year. But in the purely solenoidal, even after 0.45 million years, it still hasn't reached the 5%. That's because like the star formation rate is an order of magnitude different between these driving. So the time that is taken to reach this 5% SFP or like the end of simulation can actually change based on the cloud parameter. Even the video, when you change the virial parameter, that can also change because the star formation rate is. That said, what was that your question?